Hello and welcome to another lecture for my class, PSYC 440/640. The class is called Experimental Methods, but it's really a class that will hopefully review and deepen your understanding of univariate data analytic techniques with an emphasis on the model comparisons approach to the general linear model. This comic today comes from phdcomics.com, which I highly recommend that you follow. And it describes an experience I think many of us have in grad school or even in our current lives, where we have a little bit of coffee to wake ourselves up, and the caffeine gets us to a sort of a jittery state that in some ways may be counterproductive to writing. This comic actually really reflects some truth about the pharmacology of caffeine, and I like it so much that I think I'll borrow it or use it again in some of the lectures I teach on caffeine for my drugs and alcohol class. But that's a whole separate set of videos, and if you really are interested in that, you can probably go watch them now on YouTube. As far as this lecture goes, I'm just going to be continuing my discussion of the assumptions that we need to make, or at least we often need to make, when doing many of the tests and analytic processes that we do in psychology research. So where we left off last time, I was talking a little bit about assumptions in a very general sense, and assumptions here are just expectations that we hold about the data that we use in our analyses, and these are necessary for many of our analytic techniques, many of our tests to work properly. In large part because all of our tests involve estimating population parameters based on sample statistics, sample values. And those estimations are either going to be good or bad depending on some of the assumptions we make about our data. And the risk of being a little bit vague about it, different tests make different assumptions, and I would argue, generally speaking, that it's just important to understand what these assumptions are and to understand how the tests that we're using behave when those assumptions are not met or when they are even violated. In an attempt to organize the assumptions a little bit, I tried to highlight the idea that some assumptions have a lot to do with how research is designed and how research is conducted. Where are the designs and methods used? So if we talk about the assumption of interval data on the outcome variable, or the assumptions of independence on the outcome variable, these are concerns that have a lot to do with how you set up your study and the choices you make about how you measure your variables, especially your outcome variable in your study. Other assumptions, the ones I'm really going to focus on today, have more to do with how you actually analyze your data, or what the data looks like once you've actually gathered it. And those assumptions include the assumption of normality and the assumption of homoskedasticity. Now, in talking about assumptions, I think sometimes we can get a little bit into a vague or nebulous place, and in an effort to keep things relatively straightforward, I first want to divide up the assumptions into those two broad groups like I just showed on the previous slide. I also want to set out what I'm calling like a basic approach to thinking about assumptions and how they affect data analysis. And the first step of this approach is actually just to deal with outliers. That is, when you gather data from a sample drawn from a population, one of the first steps you should take is to examine the distribution of values for that data and try to discern whether there are any outlying or unusual values. Sometimes you can do this relatively easily, sometimes it takes a bit of work. In any case, this is a good practice. One, you should just know a bit about your data. I think it's good to kind of make friends with your data before you really launch into your analyses. And two, dealing with outliers can often mitigate a lot of the problems that can come up when we have violations of assumptions. Basically, outliers make things worse. If we can get rid of outliers and make a few other careful choices early on, we worry a little bit less about some of the assumptions that we make down the line. Next step in my basic approach is just to think about the context and think specifically, what are we making assumptions about? I know that seems like a vague question, but I'll get into a bit more of what I mean later on. Third step might be something like constructing graphs, identifying where problems with assumptions are. This is especially important for the assumptions of homogeneity, variance, and the assumption of normality, where graphing can be really useful at highlighting the extent to which those assumptions are met or the extent to which they are violated. And finally, there are, in some cases, specific statistical tests that you can use to evaluate some of our assumptions. So last time I talked about the assumption of independence, I noted that there is such a test called the Durbin-Watson test, which looks at the serial dependence of one outcome, one score on an outcome variable with the next score on that outcome variable. Today I'm going to focus a little bit on some of the tests which allow us to evaluate whether there are differences in the variance in two or more groups, and so on and so on. These tests, these sort of formal statistical tests, are useful, but they're not always as useful as we may think. In the case of Durbin-Watson, it's just a pretty limited take on what non-independence is. And in the case of some of the tests of normality and homoskedasticity, as we'll see in this lecture, those tests tend to perform best under circumstances where we worry the least about the violations of assumptions, and those tests tend to perform really poorly under circumstances where we ought to worry quite a bit about violations of assumptions. So the statistical tests are out there, but they're often not as useful as we think, and really at best I think they're maybe like the last step in a general process that you would engage in to think about assumptions that you're making in your analyses and evaluate the extent to which those assumptions are met or violated. Okay, so I gave you my basic process. Here's my overview. I'm just going to talk more about assumptions. I've already said that. Specifically, the assumption of normality and the assumption of homoskedasticity. Up first, normality and the familiar normal curve. Now, the assumption of normality can be one of those slightly tricky things to talk about, and I'm really going to do my best to lay it out in a slow and clear way in this lecture, so hopefully I succeed in that. Part of the challenge here is that normality can mean different things in different contexts. One context is the sample distribution, that is, the distribution of data that you actually have from the sample that you've drawn from the population. And to be clear right now, this data doesn't need to be normally distributed for almost anything that we're going to do in this class. It isn't the case that we have to have normally distributed data in our sample. That said, it's often worth checking to see what the distribution looks like, mostly as a way of getting a sense of whether there are odd effects in your data, unusual values, especially outlying values. So in previous lectures, I know I've talked about this. It's useful to examine a distribution of data you have in your sample. And you might well wonder if that data is normally distributed, but it is not an assumption that you have to make that the data is normally distributed or that the data must be normally distributed. So to be clear about this, normal distribution of sample data is helpful, especially if you're estimating a population mean or something like that, where or you're creating confidence intervals. It can be advantageous to have data that doesn't have a lot of outliers, because then your sample mean will be a relatively unbiased estimator of your population mean. So again, it's nice to see. It's not always necessary. And as I said on the previous slide, having normally distributed data is nice because it helps you kind of identify if there are outliers. If all the data points in your sample are more or less normally distributed, and then there's this one or two data points way off in the distance on one side, then clearly they're outliers, and you might want to investigate them. An important point here is that sometimes when researchers gather data, they check to see if that data is normally distributed. That's a good thing, by the way, but then they really worry if the data is not normally distributed. This worry only makes sense, at least to me, to the extent that we expect sample data to be normal in shape. You know, if you gathered a large sample of data for a particular variable and you had a strong expectation that that variable ought to have a normal distribution, like you were gathering some test of you're gathering data on some personality trait which we know to be normally distributed in the population, and you gathered a large sample, you might reasonably expect that that sample would have a normal distribution, and you might be a little bit worried if you didn't see that. because you might question your research methods, or if there was bias in your sampling, you gathered too many of people at one end of the distribution versus the other. And again, this worry, I've said this a few times now, makes sense to the extent that examining the distribution of your sample data is helpful for identifying odd shapes or odd values, data that's really skewed when it ought not to be, or data that contains outliers which are weird and worthy of further investigation. Bottom line, please do check the distribution of your sample data, but please do not worry, at least not worry desperately, if that distribution is not very normal in shape, unless you have strong expectations that it should be, based on the nature of the construct that you're studying. So another context where we can think about normality is in the sampling distribution. That is, the distribution of values for whatever statistic it is we're drawing from our sample. So we draw a sample and we compute, I should have said, like a mean or a t-test to compare two groups, or a correlation to look at the relationship between two variables. Now that value for that descriptive statistic or that test statistic or whatever is part of a sampling distribution. It's really part of several different sampling distributions. Those sampling distributions do have to be normal, or at least have to have a regular shape in order to do a lot of the hypothesis testing that we want to do. So we saw in the example of doing like a z-test, that test uses a normal distribution. Or there are examples like a t-test doesn't technically use a normal distribution, it uses a t-distribution, but that distribution is based or can be derived from the normal distribution. Even the kind of weird looking f distribution is based on the normal distribution, and all of these are sort of well behaved and well understood distributions. We really need that in order for our hypothesis testing procedures to work properly and to not lead us into biased conclusions. Luckily, at least based on the central limit theorem, we can reasonably conclude, or we can reasonably expect, I should say, that if we gather large samples, which are somewhat arbitrarily defining as samples of greater than 30 people or so, then we will have normally or regularly shaped sampling distributions for the statistics that we compute from our sample. It's also worth noting that having normal sample data helps in ensuring a normal sampling distribution. So the ideal situation for a researcher would be something like he or she gathered a large sample from a population, examined that sample distribution, and it looked pretty close to normal. It didn't have a lot of weird outliers or odd shape to it. And then he or she could sit back and think, well, it's important that my sampling distribution for the test statistics that I'm going to compute with this sample is regularly shaped. But I've got a large sample. The sample distribution itself is pretty normal. I feel like I'm in a pretty good position right now to do some hypothesis testing. The really important point here, I've made this a couple times, but it bears repeating, is that larger samples are almost always better than smaller samples. They're better for a lot of reasons. One of them is that the sampling distributions that for descriptive statistics and test statistics that we can make from large samples tend to be more regularly shaped. They're more regularly formed, more easily related to the normal distribution, which really helps us out in estimating parameters, conducting tests, and so on. So large samples, good. Small samples, especially small samples with weird outliers or weird shapes, bad. Now the third context in which we can think about normality is in terms of the population data. And this is a little bit abstract because of course we never have all of the population data. It's out there, but we can never have all of it. However, we usually assume that the distribution of data for almost any variable that we're studying in the population is normal. And that's just because it is, or it seems to be empirically the case that many things that we study in the life sciences, behavioral sciences, psychology, those things tend to be normally distributed or fairly close to normally distributed. So, if you gather really large samples of people and measure personality traits or measure aspects of intellectual ability or measure aspects of emotionality, what you find is that those distributions, which admittedly are distributions based on samples, have relatively normal shapes, which allows us to figure or to make the guess that in the population a lot of stuff is probably pretty close to normally distributed. Okay, are you still with me? Hope so. Normality can be thought of in different contexts. It can be thought of in terms of the sample distribution. It can be thought of in terms of the sampling distribution. That's the really important one. And it can be thought of in terms of the population distribution. There's actually yet another way we can think about normality, and that's in terms of the error distribution. That is, we can think of, and we can actually examine the distribution of errors that a model makes when predicting values of the outcome variable. And this actually is important, and we'll talk about this a lot when we get to regression in Unit 2. We assume that errors that the model makes are identically distributed. That is, they're sort of symmetrically distributed, and that most of them are relatively small. Some are relatively large in one direction, some are relatively large in another direction. This is something we definitely check. If we run a regression or we run an ANOVA, we often want to plot a histogram for the values of the residuals, the values of the errors, and see the extent to which that distribution looks pretty normal. If it doesn't, it can highlight problems where our model is biased, where it is overestimating or underestimating certain members of our sample, and presumably certain members of the population. So this is yet another way that we can think about normality. And a bit like the sampling distribution context, this one too, the error or residual distribution context, this one's also important. Okay, so what do you do about this? Well, the truth is that as we go through this class and we focus on specific examples, when we get to regression, when we get to ANOVA, we'll be practicing this a lot. But for the time being, let's just do a relatively simple example that comes from Andy Field's textbook, Discovering Statistics Using SPSS. And so to sort of paraphrase and adapt the example a little bit, imagine that you're a public health researcher who's studying personal hygiene, and you're particularly interested in people's hygiene when they go to large outdoor music festivals, which obviously are popular in America, but I think are perhaps especially popular in England. So people go camp out for a period of days, they watch shows, and over that time they just get increasingly messy from sweat and mud and the residue of all the drugs they're doing, and so on and so on. So let's imagine that you're one of these people, you're one of these public health researchers, you've gone out to study hygiene. It's a non-experimental design in the sense that what you're doing is just going to a large outdoor music festival for a period of days, and you're kind of interviewing people and making an assessment somehow of their level of hygiene. So let's assume you wanted to look at the distribution of sample data that you got, which you probably would want to do, you should want to do. To be clear, it doesn't absolutely have to be the case that this data is normally distributed, but you might sort of assume that hygiene is one of those normally distributed variables, and you might be motivated to check anyway. If this is the case, one of the first things you could do is some basic graphing. So for instance, you could make some box plots or some histograms that will allow you to do some visual inspection for the shape of the sample data, and you can kind of eyeball whether this data is normally distributed or not. By the way, if you're enrolled in my class, you can use the data set that's available on Blackboard called Download Festival. Download Festival, I think, actually is a real festival in England, for those of you who know or care. If not, if you're just watching this video on YouTube, you're not enrolled in my class, I'm pretty sure you can kind of follow along, or you could open up pretty much any data set and kind of play along with your own data. This isn't that hard. So this is our data set. You can't really see what the data looks like because it's kind of hidden behind these pull-down menus, but essentially we're using a ticket number for each person, their ticket number for the concert outdoor music festival, as kind of like their ID number, and then we have a variable that codes their gender, male or female, and then over 3 days we have a rating of their level of hygiene, which I think is on a 4-point scale. And most attendees attended the first day, fewer attended the second day, and fewer still attended the third day. So if you sort of follow the data over time, there's a lot of loss of data, which I guess kind of makes sense. Many people just decide to go home after day one or whatever else. Anyway, let's imagine you want to make some graphs. You got some different options. One thing you might want to do, I would recommend, maybe even before you get to graphing, is to sort the cases. So let's focus on day one here. Go to, in your menus, data, pull down to sort cases, and you open up the little work menu for sort cases, and you can sort the cases ascending or descending, however you like, based on the variable hygiene on day one. And just go ahead and hit OK. The reason we're doing this is to look for extreme values. So we might find a value, a case I should say, that has a value for hygiene on day one that is just outside of the range that would be possible based on the metric of our assessment. A value that's in the 20s, even though our scale only ranges between 1 and 4. Another thing we could do is make some box plots. I haven't really shown how to get here on the menus, but basically you have to click on graphs, I'm sure makes sense, and click on chart builder, which opens up this kind of workspace that we use a lot in SPSS for making graphs and charts. In the gallery tab, which is sort of in the lower left, go down and select box plot, and then just click the button on the furthest right for the simple box plot. Either double click it or kind of drag it upwards into the workspace, and then drag our variable hygiene day one into the kind of blank field that looks like it's sort of the y-axis. So hopefully my description of that makes sense. And you get a basic box plot. You can hit OK or continue or whatever the language is at the bottom of the workspace, and you'll get a box plot that looks a little bit like this. You probably remember box plots from a basic stats class you've taken. They're just ways of describing the range and the sort of dispersion of data on a particular variable. Here we have our variable for hygiene on day one, as you can see, and SPSS helpfully highlights case numbers, which are the case numbers for cases which are unusually outlying. So we see case number 809 and especially case number 810 are outliers. 810 is a ridiculous outlier because the value for that case is very, very high. It's in the 20s when, as I said before, the range of this scale runs, I think, from like 1 to 4. So clearly that's a weird value. By the way, if you're kind of old school, and I am in many ways these days kind of old school, there are other options for making graphs in SPSS. There are the so-called legacy dialog boxes. Those are in graphs, legacy dialogues, and you see here a little side menu for bar graphs, 3D bar graphs, etc., etc., etc. I remember back in the day when SPSS that's all it had. These are just different places that you can access box plots or other types of graphs. If you're comfortable with them, they give you somewhat more flexibility to do different types of graphing arrangements. I find them in some ways a little easier to use, but that's probably just because I'm familiar with them from way back in the day. So for instance here, I'm selecting box plot, and I'm selecting simple box plots that are summaries of separate variables, and I'm clicking the define button, which opens up the little menu on the left of the screen, and I'm saying give me box plots for all 3 days, and so on. I'm hitting OK, and I can get box plots for all 3 days of the download festival. So not just day 1 separately and then day 2 separately and day 3. I got them all on one image. So maybe that's better. Also here I've asked SPSS to tag cases that are outliers by their ticket number. So rather than using case number, which just is the number of the row the particular case is in, which might change depending on how you sort the data, I'm now using ticket number, which, as I described earlier, is the unique identifier for each participant in our data set. So this person here, who I think before was case number 810, yeah, that's person's ticket number is 4158, and again we see that whoever he or she is a massive outlier, probably because there was some sort of data coding problem. Just a little interesting side point here. SPSS, if you're new to SPSS, it just seems like this kind of sort of maybe slick integration of different types of statistical analyses. Really, it's an absolute hodgepodge of newer and older modules and functions all kind of built on top of each other. So for example, there's the somewhat newer way to make box plots in the chart builder, and then there are all these legacy ways to do it. And as you may have noticed earlier, and as you certainly will notice as the semester goes on, there are sort of redundant ways to get at the same types of analyses. And that reflects somewhat the kind of the history of how SPSS was developed. Over the years, programmers working for the different companies that have owned SPSS kind of write different programs that sort of subsume or take over from others. And if you're a new user in the year 2017, you might think, oh gosh, why are there like 4 different ways to do an ANOVA? Or why are there like 2 or 3 different ways to get a box plot? Well, it's just because the thing grew up over time. It evolved in some weird haphazard way. Another interesting point, or kind of, I guess, relevant point to make right now is if you really paid attention to those menus on my previous description of the legacy dialogues for box plots, you might have seen me selecting options for getting rid of cases. Now, the idea here is that we don't have complete data for all cases in our data set for all days. So some people went to the festival and stayed for day 1, day 2, day 3, so we have complete data for those folks. Some people left after day 2, so they have incomplete data. Some people left after day 1, we have even more incomplete data. When faced with those problems, we sometimes want to reduce our data set or get rid of or do something with cases who have missing data. It's less of an issue for this particular example because we're not really testing a specific hypothesis, but if we were testing, let's say, some sort of repeated measures ANOVA and we had missing data, that could be a huge problem. And generally speaking, there are 2 sort of approaches you can take for graphing and for analyses when you have missing or incomplete data. The first is called case-wise deletion. So case-wise deletion is any case, any particular person, it's usually a person, who has any amount of missing data, we delete that person entirely. So if someone had data for day 1 and day 2 but not day 3, we get rid of them. So they're deleted or removed or filtered from our data set. The other option is variable deletion. So we only delete cases for analyses where those cases are missing data that are needed for those analyses. So we don't delete a case that has missing data for day 3 if we're doing analyses only based on day 1 data or day 1 and day 2 data. But if we do analyses based on day 3 data, then of course we delete that case. Case-wise deletion is the more severe approach. Like if you're missing A data, you're dead. You're dead to me data, or you're dead to me case. Variable deletion is like, well, maybe I'll keep you in my analyses, maybe I won't, it kind of depends. And I know that sounds a little silly to explain it that way, but there are kind of pros and cons of either approach. There's also a whole very interesting sort of area of applied statistics that involves imputing values. Like if you have missing data, you can kind of in a sense guesstimate what that data should or would have been. We'll probably not get to that so much in this class, but it exists. Suffice it to say, for right now, for graphing data as we are, we might either do case-wise deletion for this unusual case with this weird outlying value, or cases with missing data, or we might do variable deletion. So particularly this person with case number 4158. Now, this person doesn't have missing data. At least I don't think she has missing data, but she's weird because she's an outlier on the variable for day 1 hygiene. And so again, we can apply this logic of case-wise or variable-wise deletion. We should be examining this case because she's an outlier, and we might wonder what went wrong here. It's probably the case that there was just some coding error. The person who was interviewing her should have given her a 2 for the variable but accidentally wrote 20, and maybe if we found out that to be the case, we could just change the value of the data. But for the time being, let's just assume there's a good reason to get rid of this person. She's an odd person. We're just going to delete her. So you can go ahead, just go into your data set and delete that case, or, and we'll talk about this a little bit in the future, there are ways to filter the data set so as not to actually delete the case but just sort of remove it from analyses. Anyway, after getting through all that, let's just go ahead and again consider some graphing options. We've looked for outliers, we found an outlier, we talked a little bit about options for keeping or deleting cases. Now let's go ahead and make some graphs to look at normality. Here there are different options. One is to go to Analyze Descriptive Statistics Frequencies, which opens up the little frequencies work area. Take the variables for day 1, day 2, day 3, put them into the variables field, click on charts, and you can ask for histograms with a little check to say show normal curves on histograms. Hit continue, hit OK. And you'll probably get some output that looks a little bit like this. I've kind of squeezed them down to put them all on one PowerPoint slide, but if you're looking at SPSS output, these will be a little bit bigger. And you can see that across the different days, the data looks more or less normally distributed. On day 1, where we have a very large amount of data, perhaps unsurprisingly, the distribution looks closest to the familiar normal curve. On subsequent days, it's less so. Now, having the normal curve superimposed over the histogram is helpful, but it can still be a little bit tricky to eyeball the data. I mean, in the case of day 1, we're like, yeah, that looks pretty normal, but what about day 2? It's kind of normal. I'm not sure. Is there another way to think about this data? Well, there is another way to think about this data. You can go to Analyze Descriptive Statistics PP plots, or probability plots. That'll open up a new workspace, and you can put our variables, hygiene, day 1, day 2, day 3, in the variables field. And we have a lot of options here for comparing the distribution of these variables to different other distributions that are known. So in the case, you can kind of see on the right, we can have what's called a test distribution. Imagine normal is probably the default, but you can select among a number of different mathematically known distributions and select normal. Distribution parameters are estimated from the data. Check that box. You can kind of ignore some of the other options here for the time being. Hit OK, and you'll get some output. Now the output you get are called probability, or PP plots. And what they do is they represent the cumulative probability of the variable, of the data for the variable, against the cumulative probability of data in a known distribution, in this case, a normal distribution. So if you look at the output for the PP plots, you first get this output called estimated distribution parameters, and these calculations of location and scale, they're just really the mean and the standard deviation for the distribution. Since these are estimated from the sample, they're just the sample mean and the sample standard deviation. The more interesting output are the PP plots themselves, and they work a little bit like this. The line that you can see, especially in day 2 and day 3, is the cumulative probability of the data if the data was in a perfectly normal distribution. The little circles, little sort of hollow dots, if you will, those are the actual observed values of the data, the cumulative probability of those observed values. And if those dots line up on the line, then the data is normally distributed, or pretty closely follows a normal distribution. To the extent that they drift away from that line, it's indicating the direction and the sort of the presence and the direction of a deviation from normality. You actually also get some other output called detrended PP plots, which just help us to kind of examine the magnitude of those deviations from normality. They kind of emphasize how big the drift is, if you will. And you can see in the case of our day 1 data, the drift off of normality is very slight. In the case of day 2 data and day 3 data, it's more so the case. So let's just consider the day 3 data. Here's where we've got a pretty big drift off of normality. By putting these graphs together, you kind of get a sense of where the deviations from normality are and where they are the biggest. It certainly looks like kind of in the middle of the distribution, we've got this rather large deflection or drift off of normality. By the way, if you're working in SPSS output and you double click on a chart or a graph that's in your output area, it'll open up the chart editor, and if you use the little bullseye symbol, or little bullseye button that's kind of in the upper left, it'll allow you to kind of bullseye or highlight different case numbers. So you could zero in on any one of those dots, click it, and you would get the case number for that data, or that data point, or those two data points in this case, because they're superimposed over each other. Remember, case numbers are just the number of the row that the particular case is in, and that will change depending on how you sorted the data. But let's imagine that you were curious, like, wow, who are these people who are so so far off of this normal distribution? Well, you could click on them and you'd see that, well, there are lots of them, but these two that I've clicked on are case number 542 and 772, which could be useful for identifying potential outliers. It's really less so a value here because almost all the data is pretty weirdly distributed. But if you had data like the day 1 data that was really well distributed normally, but you had one circle or one dot way off on its own, you might think, who's that person? It's just another tool for for identifying potential outliers. So one approach to evaluating normality is graphical analysis. You can make and examine some graphs, whether they are box plots or histograms with normal curves superimposed on them, or PP plots or detrended PP plots. That's a good approach, I think, because again, many of us enjoy looking at pictures, I suppose. It's kind of silly, but we're just normal people. We like to look at pictures, and pictures can give us important information. There are other ways that we can examine normality. Particularly, we can examine the extent to which a distribution is skewed or kurtotic, how much it drifts away from what we'd expect for a normal distribution. And specifically, we can do a z-test, just the good old z-test, to examine whether our distribution has a skew that is different from what we would expect in a normal distribution, or a kurtosis that's different from what we'd expect in a normal distribution. In order to do this, we just are taking advantage of the fact that a normal curve, by definition, has 0 skew and 0 kurtosis. So if our skew or our kurtosis are not 0, it probably will be not 0, we can ask, is this difference statistically significant? And the z-test is just the observed value minus the expected value, which is going to be 0, because the expected value is 0 if the data was normally distributed, divided by the standard error of either the skew or the kurtosis. And again, if z-test for skewness and kurtosis, if the values that we get back are greater than 1.96, then we know that our test is statistically significant at a level of 0.05. So we can say, oh, this data is distributed in a manner that is significantly more skewed than we would find in a normal distribution. Now, one of the challenges here, though, is getting those values for skew, and especially standard error of skew, or kurtosis and standard error of kurtosis. Those are probably not calculations that you know off the top of your head, but happily in SPSS we can get them. So one of the ways we can do this is go to Analyze, Descriptive Statistics, Frequencies, go to the Frequencies work area, highlight the variables you want, then click on the Statistics button and ask for measures of central tendency. Ask for measures of distribution. Here I've clicked a whole bunch of stuff I don't really need. If you're only interested in skewness and kurtosis, you could just ask for skewness and kurtosis in the bottom right, but as is my way, I highlight a whole bunch of stuff, hit continue, hit OK, and depending on what you ask for, you'll get a lot of descriptive statistic output. I've just highlighted here these values for the skewness and the kurtosis and their respective standard errors across the different days. So you can see those values there highlighted. And for some reason I also highlighted range, but that was an accident. Okay, so let's do some z-tests. And here I'm just focusing on day 3 because I have enough space on my slide to do the z-tests for all of the days. So if we're doing some z-tests for skewness and kurtosis, we just take those values for skewness and kurtosis and their respective standard errors, and we plug them into our calculation, and we get values that look a little bit like this, which suggests that the skew is significantly different from normal on day 3, and the kurtosis is probably not significantly different at least not at our alpha level of 0.05. Okay, so are you with me so far? We're examining the assumption of normality. We're focusing here on sample distributions, and really there's not a strong assumption of normality in sample distributions, but let's just say we're curious about the distribution of our sample data, and we want to know, is it normal or not normally distributed? There are different approaches we can take to evaluating that. The first is to make some graphs and just look at them. The second approach is to do some z-tests for skewness and kurtosis. That's useful. The third approach is to do formal statistical tests, and there are some options here. One is the Kolmogorov-Smirnov test, and that is a test that I'll show you in just a second. Basically, it returns to us a test statistic value and an associated p-value. If the test is not significant, if p is greater than 0.05, then the distribution is not different from normal. If the test is significant, then the distribution is significantly different from normal. That's the basic gist of the interpretation. So there's also the Shapiro-Wilks test, which is a test that in some ways is a little bit more sensitive than the Kolmogorov-Smirnov test, but for the most part they kind of work the same, at least for our purposes. How do you do these tests? Well, they're hidden somewhat in the Explore work area. So Analyze Descriptive Statistics, Explore. I like the Explore module. I think you get a lot of interesting stuff here. So I tend to do a lot of my descriptive statistics work here for what that's worth. I'm going to put all our variables in the dependent list. That's what Explore module calls the variables that are the outcome variables or dependent variables you're looking at. I'm going to click on the button for plots. For some reason, the normality plots and tests are hidden here. So click on the little checkbox for normality plots and tests. If you also want, you can ask for some box plots or some histograms, stem and leaf stuff, things which you encountered in other modules like the frequencies module. Those are hidden there too. Hit continue, hit OK. You'll get a whole load of output. I'm going to focus just on the output for the tests of normality. And you can see here that we have the Kolmogorov-Smirnov test, the Shapiro-Wilks test. I'm focusing just now on day 3 again, and you could report the value of the test statistic and the degrees of freedom, and you can report the p-value, and you can say, well, this data for the day 3 hygiene is significantly different from normal. It's significantly different for all the other days as well. But again, I'm just focusing on day 3 for the time being. Now, way back at the beginning of the lecture, I mentioned that there's a potential problem with these formal statistical tests of assumptions. And the problem really boils down to the fact that they are themselves hypothesis tests. And like any hypothesis test, we have to consider the power they have to detect effects. In this case, the effects being deviations from normality. And the problem is, in large samples where we have lots of power to detect deviations from normality, we probably don't worry about deviations from normality all that much. Because again, the distribution of our sample data, its shape is not desperately important to us. We don't make a strong assumption or levy a strong requirement that that data be normally distributed. Rather, we just look at it out of curiosity or in an effort to find outliers or unusual cases. So in situations where we have a lot of data, our test for normality gets really powerful, and even small deviations from normality will be statistically significant. So our Shapiro-Wilks or our Kolmogorov-Smirnov test will come back p less than 0.05. But in those very same samples, which again are large, we don't worry about it too much because large samples tend to give us normally distributed or regularly distributed sampling distributions for our test statistics under the central limit theorem. So it's like when we're really good at finding differences from normality, that's exactly the time when we probably care about it the least. In comparison to that, if we have small samples, then our tests, the Shapiro-Wilks test, the Kolmogorov-Smirnov test, have very little power to detect deviations from normality. They're not good at finding deviations from normality, and those are the situations in which we probably care a little bit more about our sample distribution, because non-normally distributed sample data is not a big deal unless your sample is really small, because then you start to worry about the extent to which descriptive statistics like means or test statistics like t's or f's or chi-squares are going to be unbiased estimators of population values for those calculations. You worry about it more in a small sample because you feel less comfortable that the sampling distribution is going to be normal or regularly shaped. So right then it would be really good to know if your data is different from normally distributed, it's distributed differently from normal, but at that very moment you have very little power to detect any deviations. So you probably should be worrying, but you can't, at least using those tests, detect. Just to remember though, sample distributions don't have to be normal, although it's often nice to see them normally distributed. Error distributions probably do, and I haven't really talked about this so much, but we could use this same approach to examining a distribution of residuals, and we'll do this actually in the unit on regression. So rather than sort of obsessing about the distribution of our sample data as we did in this silly little example, we might get SPSS to give us, as in a separate column of our data set, the residuals for our module. Or I'm sorry, for our model, and then we could make graphs of them, or we could do z-tests on them, or we could do formal statistical tests on them to see how normal or non-normal they are. So what you've learned so far, hopefully learned so far, will be important, or it is important, for example, especially when we're looking at residuals, which admittedly I haven't talked about too much yet because we're not yet in the unit on regression. Okay, let's move on a little bit now. Let's talk about homogeneity of variance, or homoskedasticity, if you want to use a really fussy sounding word. This assumption is also a little bit confusing, at least potentially, because it means different things in different contexts, a little bit like our assumption of normality. One context is in the terms of the sampling distribution. So we might look at the variability of our outcome variable if we have different groups in our data set. We might look at the variability on that outcome variable among those different groups and ask ourselves, is the variability in the one group similar to the variability in the other group? And in this context, homogeneity of variance is helpful. Assessing it helps us to find outliers. Gosh, the variance in one group, variance just being variability with respect to the mean, in one group is really different than variance in the other group, but that's because the first group has this weird outlier which is pulling off the mean and disrupting the calculation of variance. So kind of like we saw with the assumption of normality, one of the ways in, or the kind of the approaches we might take, is to use our consideration of assumptions as a way to think about outliers first, or look for outliers first. That's almost always a valuable thing to do. It's an important point here. In sample data, we hope that variances in different groups are equal. So if we have a categorical predictor variable like treatment group versus control group, we might well hope that the variance on the outcome variable is similar in the one group as in the other group. Now their mean levels of the outcome variable might be very different. In fact, we probably hope they're very different, but the variances should be pretty similar. Even if we have a continuous predictor variable, we hope that the variance on the outcome variable is similar at different levels, or at different points along the range of that predictor variable. To be clear, we should check this, and we will check this in our unit on regression, our unit on factorial designs. We should do it because tests, when this assumption is violated, when variance is different in different groups or at different points along a continuous predictor variable, our estimation can go off, or our statistical tests can be biased in terms of the conclusions that we draw from them. Now, at this point, it's worth mentioning that some tests, like ANOVA, for instance, are often described as being robust to violations of the assumption of homogeneity of variance. And this is true to some extent, but only when group sizes are equal. And as I'll discuss, I don't know if I do it in this lecture, I know I do in a later lecture, when group sizes are unequal, it's really, the violations of assumptions of homogeneity variance get really problematic. Now we can also consider homogeneity of variance at a population level. So again, we imagine like in the population there's a group of people who get a treatment and a group of people who do not. We don't have all the data for these two groups, but they in principle exist, and we usually assume that the variability on whatever our outcome variable is the same. Make this little sort of rhetorical question here. Is this always the case? For instance, in medication trials, maybe this isn't. It might be sort of a bit foolish to assume that on our outcome variable, like say its level of functioning, people who receive a particular drug or treatment are going to have the same level of variability in their response and their outcome as do people who do not get the treatment. That's maybe a tenuous assumption. And we can also consider homogeneity of variance in terms of, or in the context of, errors or residuals. So kind of like we were talking about before in terms of normality, we're assuming that the variability of the errors is consistent across different groups or different levels of our predictor variable. So if you have a hard time visualizing this, here's a simple scatter plot, obviously. Imagine the x-axis is some continuous predictor variable, the y-axis is some sort of course, continuous outcome variable. And where you can see the model there, it's a simple regression line, and the errors are all the sort of distances between the data points and that line. You can imagine drawing little drop lines from all the data points to the line that is the model. And you can sort of eyeballing that, you can see that there's a certain amount of error at a very low level of prediction when the predictor variable is rather low, and there's a certain amount of error when the predictor variable is relatively high. We're assuming that the variability of those errors is about the same. Like if we took a line and slid it up and down the model, the amount of variability would be comparable at any point of that line. If you're having a hard time visualizing this, still, here's a kind of another take on it. Here's our simple model here, our predictor variable and our outcome variable. We're assuming that the distribution of errors or residuals is about the same in terms of its spread or its dispersion at a low level of prediction, at a moderate level of prediction, and at a high level of prediction. And indeed, technically, at any point along this line, we'd have about the same level of variability in our errors or our residuals. So to summarize this a little bit, we want the distribution of errors within each level of a predictor variable or at each point along a continuous predictor variable to have the same variance. And this is something we definitely should check. Heterogeneity of variance or heteroscedasticity can highlight places where our model doesn't work well. For instance, where it makes really large errors. Like imagine that you have a continuous predictor variable, and at low levels of the predictor variable, the errors are relatively tightly constrained. They're not broadly dispersed. However, at high levels of the predictor variable, the errors are very highly dispersed. That tells you, and you could see this if you graphed it, that the model makes fewer or smaller errors at low levels of the predictor variable and more at high levels of the predictor variable. That would, that I think you can almost appreciate on an intuitive level. That suggests that the model works well at low levels of the predictor variable. It doesn't work so well at high levels. Another example would be, imagine your predictor variable is not continuous, it's categorical. So you have two groups, let's say a treatment group and a control group, and if the variability in the one group is very small, variability in the other group is very high, it suggests to us that the model, which is describing the relationship between group membership and the outcome variable, works better or makes smaller errors if you're in one group than it does in the other group. And I think, again, at an almost intuitive level, you can understand that that would be problematic if you had lots of heterogeneity of variance. So to summarize a little bit more, I guess I'd say homogeneity of variance means different things in different contexts. We can think of it in terms of our sample distributions, in terms of our population distributions, which again is a bit abstract, and in terms of our error distributions. And it's somewhat different if we're talking about a continuous predictor variable or a categorical predictor variable. Just to highlight that point one last time, we'd say for a continuous predictor variable, the variance, which is variability with respect to a mean, of the outcome and the errors should be consistent across the range of prediction, across the range of the predictor variable. For categorical predictor variables, the variance of the outcome and the errors should be consistent in all groups for the predictor variable. Okay, so you're thinking, I get it, sort of, homogeneity variance, it's important, it means sort of different things in different contexts, but in any case, it's something that I should probably look at. How do I do that? Well, the approach is similar to how the approach we took for the assumption of normality. We might begin by making some graphs. And in the case of a continuous predictor variable, probably the easiest thing to do is make a humble scatter plot. At least if we have a simple regression where we have one predictor variable and one outcome variable. Admittedly, this gets a little bit more challenging if we're doing a multiple regression. We have multiple predictor variables. But we can still, we'll talk about this in the next unit, but we can still make a graph to represent the relationship between the model and the outcome variable, and we can look to see where there is lots of variability in errors, residuals, and where there is little variability in errors or residuals. If we're thinking about categorical predictor variables, box plots or even histograms could be helpful just for highlighting how variable the data is. Here we've got 5 different, well, they're different groups, let's say, and we have the variability on the outcome variable in each one of them, and you can see in some groups there's quite a lot of variability, in other groups there's less, and because we're making box plots, we also have the nice highlighting of outlying cases which we might want to examine anyway. So one approach we can take to evaluate the homogeneity of variance assumption is to do some graphing, look at some pictures. Another approach is to do some formal statistical tests. And the one that applies here is Levine's test. And the logic is very similar to that of the Kolmogorov-Smirnov and Shapiro-Wilks test for normality. If Levine's test is is statistically significant, if p is less than 0.05, then the groups have significantly different variance. If the test is not statistically significant, the groups do not have significantly different variance. Another approach we can take is to calculate Hartley's Fmax, which is just the ratio of the variance in the group that has the largest variance to the variance in the group that has the smallest variance. And as I should have said this on the last slide, but basically these tests, Levine's test, Hartley's Fmax, only really work, they work most easily in situations where we have a categorical predictor variable. In the case of Fmax, you can imagine, I think, pretty easily that larger ratios, larger values for the calculation mean bigger problems. And you can actually find online very easily tables for Fmax, like how big, based on your sample size, is a really big Fmax value such that you probably have a significant difference in variability between two groups. So another calculation you can do, very easy, kind of works in a similar fashion to Levine's test. Okay, so I want to quickly run through an example of how you might look at the assumption of homogeneity of variance. And for this one, I'm imagining that you're a pharmaceutical researcher studying a new drug using, I think now, our rather familiar, almost kind of generic, simple experimental design where we have a treatment group and a control group for some medication. Obviously, the people in the treatment group get it, the people in the control group don't. Maybe they get a placebo dose or something else to create the counterfactual. If you're in my class, you can find this data set online. It's called antidepressant. It's just fake data that I made up. If you're not in my class, if you're just watching these videos on YouTube, thanks, by the way. Probably should say that more frequently. But you can, I think, follow along pretty easily with how this works. So first thing you might be wondering is, wait, aren't we supposed to deal with outliers? Shouldn't we have worried about outliers first? You made such a big deal about outliers in the last lecture and earlier in this lecture. Yeah, technically the first thing we should do, whether even really before we worry about normality per se or homogeneity variance per se, is look for outliers. For the sake of not making this lecture any longer than it likely will already be, let's pretend we just skipped this step. It's a bad thing to skip, but let's just say we did it. We've got a categorical predictor variable, it's treatment or control. So if we're going to examine the assumption of homogeneity variance, we can do this some different ways. My favorite way would be to use the explore function in SPSS. So go to Analyze, Descriptives, Statistics, Explore, open up the Explore work area. The dependent list is our outcome variable, depression. We're looking at the effect of the drug on depression. And our factor list is our predictor variable, or our independent variable, which is group, whether you got the treatment or the control. So that's how you kind of set up those variables there. Then click on the box for the button for plots and ask for a histogram. I don't really like stem and leaf plots, so I didn't ask for that. Ask for some box plots with factor levels together. Ask for normality plots with tests, and then ask for the spread versus level with Levine's test and hit continue. Once you've done that, go ahead and click the button for statistics and ask for descriptive statistics and ask for outliers and hit continue. The explore function is handy. There's a lot of good stuff here, which is why I find myself going back to it again and again. A lot of times when I'm exploring data and trying to look for outliers and trying to evaluate assumptions that I'm making and so on and so on. That's why I like it so much. Anyway, you've done all that. Let's move on. Let's look at the output. Hit OK. You'll get a lot of output. I'm just highlighting a few pieces here. First off, we see some evidence, at least graphically, of heterogeneity of variance. The variance in our treatment group is larger than the variance in our control group. Maybe because we have some outliers. That margin of error is quite large, for the standard error, the estimate in the treatment group. Maybe we should have looked for outliers first. By the way, this phenomenon is fairly common, where we have differential response to treatment. We often find in drug studies or psychotherapy studies that there is greater variability among the people who got a treatment than among people who didn't. There's some people really respond to the drug, some people don't. That group will tend to vary a lot with respect to itself. People in the control group, they're all in sort of the same situation. Nothing is happening to them, so they tend to be less variable. Moving down the line, you probably have in your output your tests of normality, if you asked for them. And here's just interesting to note that our tests of normality kind of give us a split decision, if you will. If we look at the Kolmogorov-Smirnov test, it is not significant, suggesting that within each group, treatment and control, the distribution of data is not significantly different from normal. But the Shapiro-Wilks test gives us a sense that in the treatment group, the distribution is significantly different from normal. But we have a really small sample here, so we have really low power to detect differences or deviations from normality. I wouldn't spend a lot of time worrying about the fact that one of these tests gave us a positive result, if you want to call it that, and the other a negative result. It's just interesting to note that it's there. Here's our test of homogeneity variance. We are allowed to, or we're encouraged to kind of consider homogeneity variance with respect to different measures of central tendency. Whether we want to think about it with respect to the mean of each group or the median of each group or so on. We don't have a lot of evidence for violations of homogeneity of variance. The groups have, at least according to this test, pretty similar variances, especially with respect to the mean. However, as with the Shapiro-Wilks and Kolmogorov-Smirnov test, this Levine's test of homogeneity of variance is probably pretty underpowered given how small the sample is. Going down the line, if you asked for it, SPSS will give you outliers, or what it calls extreme values. So it'll just give you the 5 cases that have the highest values and the 5 cases that have the lowest values for each of our groups, our treatment group and our control group. And this is useful for kind of eyeballing the data to see if there are values which are unusual or which couldn't occur. In this case, I kind of made up this data, so I'm not exactly sure why I thought the metric of the outcome variable is. I think I'm probably just imagining it's like the Beck depression inventory, and all these values you see here from lows of 11 to highs of 20 are certainly possible or even likely within the range of that measure. But let's say that one of the people in the treatment group had a depression score of -5. Well, that's clearly something wrong there, and I would go back and check my notes and evaluate what went wrong. So again, useful for looking for outliers, potentially. Let's try and review and put this all together. Putting it all together, there are different assumptions. Here we've been focusing on normality and homoskedasticity, homogeneity, variance that is, and there are different ways of examining them. Broadly speaking, there are graphical approaches and hypothesis testing approaches. One last time, let's remember the problem with hypothesis testing approaches. In large samples, they tend to work well because they have a lot of power to detect deviations from normality or deviations from the assumption of homogeneity variance, but often these assumptions or violations of these assumptions, deviations from these assumptions, are less problematic in large samples. Maybe not unproblematic, but less problematic. In small samples, these tests have little power to detect deviations or differences, but it is in these small samples that we're probably more worried about those deviations or differences anyway. Probably, you could wrap this back into the argument of you ought to have large samples. There are all sorts of reasons to have large samples. Here's just yet another one, I suppose. Maybe the more important point, or an important point to emphasize here, though, is don't just look at the Shapiro-Wilks test, or don't just look at the Levine's test and be like, oh, well, neither of them are significant, so I haven't violated my assumptions. You should probably do a bit of graphing and do a bit of thinking and see if you really feel comfortable in making those assumptions for the data you have and the types of analyses you want to do. What do we do about all this? Well, collect large samples, make sure groups, if we're using categorical predictor variables like treatment groups and control groups, make sure they're large, make sure that they are equal in size. I'll talk about this a lot more when we get to Unit 3 on factorial designs, but when we have unbalanced designs where there are more people in the treatment group and less in the control group, or vice versa, it creates all sorts of challenges to maintaining these assumptions, and sometimes it can be really difficult to resolve. As I've said a few times now, use graphs and hypothesis tests, maybe especially graphs. The emphasis here is on the and. Don't just do the hypothesis tests. Make sure you include some graphing as well. And always investigate outliers. Gosh, if I've said it a dozen times, I'll probably say it 24 times before the end of this semester. Always look for those outliers. So again, review, more review, review of the review. This time around we talked a lot about assumptions, focusing on normality and homogeneity variance. In the next class you have an exam, though if you're not in the class you don't, or at least you don't have an exam from me. And if you're in the class but you're just watching this lecture later, of course the exam is long since passed, but just to be aware that it's coming up, and if you haven't started studying, do study for it. Otherwise, take it easy. And thank you, as I always say, for watching my videos. I really do appreciate it. I know this stuff isn't super exciting, but I hope you learn. I learn when I think about this stuff, when I write about this stuff, when I try and explain about this stuff. Hopefully you learn too. So, bye-bye.